Hi guys, I'm Alex, and today me and my friend with Taqiuddin will present about multiplexing and spreading. So I will start on multiplexing. I will give a briefly general view for multiplexing. So the red color represents a single channel, and a multiplexer can receive many channels or input and combine it into a single link or n channels. So after the link transport to the destination, the demultiplexer will separate the link back to their each channel. So it's n input. So there are three types of multiplexing: frequency division multiplexing, wavelength division multiplexing, and time division multiplexing. And the orange color one, frequency division multiplexing and wavelength division multiplexing, are analog multiplexer, and time division multiplexing is the digital multiplexer. And now I will show you the flow of FDM. So first, the analog signal will generate it by its own sending device, and it's sent to the multiplexer, and then the multiplexer will modulate it with different frequency. So after modulate it, this modulate frequency will combine it by the multiplexer and make it become one link. And then after transport to the destination, the FDM demultiplexer will separate the link back into their own carrier frequency through filter, and they will separate it back to their own analog signal. Okay, analog hierarchy or hierarchy system also use of FDM. So basically the analog hierarchy is used by the telephone company which to maximize the efficiency of their infrastructure by multiplex the lower bandwidth onto the high bandwidth. So I will show you an example of the flow of it. So first, the red one represents a single voice channel produced by the phone, which is a 4 kilohertz each. So the first multiplexer will multiplex 12 channels and make it become a group. So a group consists of 12 voice channels, and it is 48 kilohertz. So when it comes to the second multiplexer, the multiplexer will multiplex 5 groups. So each total 240 kilohertz and consists of 60 voice channels. And same things, the multiplexer will multiplex it again and multiplex 10 supergroup, become master group. So a master group consists of 2.4 megahertz and 600 voice channel, and same things go on and on. So multiplex again and become a jumbo group. So it consists of 14.4 megahertz and 3600 voice channel. Thank you.
Alright, how's it going everyone? Taki here. Today we're going to talk about wavelength division multiplexing, WDM for short. So WDM is an analog multiplexing technique to combine optical signals. Optical signal is an electromagnetic signals which frequency are very high in order of terahertz. And optical signal is measured in terms of wavelength to be more convenient. WDM is designed for high data rate capability of fiber optic cable, since optical fiber data rate is much higher than data rate of metallic transmission cable. So WDM is used to is the method to increase capacity of a single fiber. WDM is basically the same with FDM, frequency division multiplexing, except it involves optical signals in multiplexing and demultiplexing through fiber optic cable. And the frequency is very high compared to FDM. The concept is simple. This diagram shows many optical signals combined into one through multiplexing. And then, vice versa, one optical signal at multiplexing split into many through demultiplexing. It sends from the transmitter to receiver. The example of optical signal is light. Combining and splitting of light can be done by using prism. As we learned from our previous school, light is made up of lots of color. In this diagram, many light beams are converged into one, producing one white light beams. So vice versa, one white light beams can be split up to many light beams. Now there's another method that can multiplex a huge amount of channel by spacing this channel very close to another. This method will further increase the efficiency, and this method is actually called dense wavelength division multiplexing, for short DWDM. Right, that is all from me.
Hi, my name is Mawat. I will be talking about time division multiplexing. Time division multiplexing is digital multiplexing techniques used to combine several low rate channels into a high rate one. In time division multiplexing, time slots are grouped into frames. In a particular frame, a slot is dedicated to each sending device in the connection. Now, if there are 4 lines of connection, then each with T time input, there will be T out of 4 time slots output. This example here shows what I just talked about. We have 4 channels, each sending data. So for channel A, the data is grouped into T time slot. Now for the output of the channel A, in frame 1, the time T is now becoming T out of 4. That means the time of the output slot is n time. The time of output slot is n time shorter than the time of input slot. This is the entire connection here of the 4 channels. Now, for the time division multiplexing is divided into 2. There is synchronous and asynchronous time division multiplexing. Basically, the difference is that in synchronous time division multiplexing, we separate frames according to the time. Okay, in the synchronous time division, a unit occupies 1 input time slot. Now, the duration of 1 output time slot is n times shorter than the duration of 1 input time slot. If we have 4 channels, each with time t, then the duration of the output time slot will be t out of 4. Now, from synchronous time division multiplexing, as I said before, if you allocate a time slot for every channel that is sending, sometimes some channels are not sending any data. So the time slot will be allocated when there is no data being sent, which is a waste of resources. Now, for example, here, the 4 channels are sending data. For channel 1, it is using the full link, but for channel 2, some slots that don't have data to send. But this slot will be dedicated time slot in every frame. So this is what I was talking about. To avoid the problem in the synchronous time division multiplexing, people introduced asynchronous time division multiplexing, where slots are allocated based on demand. For example, if this channel, channel 2, is not sending any data in this particular time slot, there will be no slot dedicated to that particular time slot in the output time slot. However, to identify which output connection has this specific time slot, people use addressing in a synchronous time division. So every bit send, every slot send will be having a header as address to where this data is being sent to. In a particular link, for example, if we have n bits, to define n output line with n is equal to log 2n. This means like if we have 16 output line, we need 4 bits address for each frame.
Multiplexing to spread spectrum. My name is Izzat. I'm going to explain about spread spectrum. First of all, there's two differences between spread spectrum and multiplexing. For multiplexing, most of the time, the signal is transmitted through physical medium. For example, cable. But for spread spectrum, most of the time the signal is transmitted wirelessly through open air. Therefore, for the second differences, the spread spectrum is more focused on the security since it's transmitted openly. So the spread spectrum is transmitted openly. There is chance where people or the enemy might actually eardrop you or even jam your signal. But for multiplexing, it focuses more on the efficiency since it's transmitted through physical medium. There is two kinds of spread spectrum. First is frequency hopping spread spectrum, and the second one is direct frequency spread spectrum. For every spread spectrum, they contain a pseudo-random code generator which is called the pseudo-random noise. This pseudo-random noise is going to create a pattern for every hopping period. In this case, for frequency hopping spread spectrum. For direct frequency spread spectrum, it's going to also generate, but for different purposes. The pattern will repeat every cycle. There's 2 cycles provided, but there's 8 hopping code. So for every hopping from 700 frequency 700 kilohertz to 900, that's one hop. So it's going to hop 8 times before it actually repeat the cycle again. So it's actually one of the way to counter the jamming or eardropping. As you can see there, signal hop from one frequency to another. So if anyone try to actually jam the signal, they can only jam a part of the signal. Even if people try to eardrop you for any meticulous reason, they can only take a little bit of your signal. For this example, I only show you 8 hop, but for the real life, there are probably more than 8. This 8 is just a little bit for just a small amount, for example. Alright, but you can see in the graph, for frequency hopping spread spectrum, it's not efficient. You can see a lot of hole or a lot of place you can actually fit in the another frequency. So another channel. So to count spread spectrum, you can see the left table, the frequency division multiplexing. They feed in 4 channel at the same time. So it's just the same as frequency division multiplexing, but the difference is it's going to change place, which means it's going to hop every interval based on the pattern. So even if outsiders receive the information, it's just going to receive a little bit of your information, just a small part. This is for example purpose, so we only show 4 frequency, 4 channel. For the real life purpose, it's going to be more than 4 channels, so it's going impossible for them to actually take and compile every frequency or trace every frequency. So this is one of the security measures that provided in frequency hopping spread spectrum. That's all from me. Thank you.
Hi folks, I'm Mabor again. I'm going to start from where my friend Izzat stopped. So direct sequence spread spectrum is what I'm going to talk about here. Direct sequence spread spectrum is one of the techniques for spreading the frequencies across spectrum. How is it done? How is it different from frequency hopping spread spectrum? The concept here is that you take original data signal, multiply it with a pseudo random noise spreading code. What this means is that you assign a secret code to each data signals that you want to send, and then you use that spreading code you assign to the original data signal to modulate the signal, and you get a bigger signal that has higher chip rate than the data rate. So you take the original signal, you assign it with the spreading code for that specific signal, then you modulate it using the modulator, and then you get the chip rate which is higher than the data rate of the signal, and then you send that modulated signal which is bigger than the original signal, you send it to the receiver. So basically how this is coded is based on the polar non-return to zero encoding. You use the exclusive OR to get to add up the original signal with the assigned code. So you take the input, which is the original signal, and then it's going to be modulated. Then you add using the exclusive OR, then you get the transmitted signal. So this signal is higher, has a chip rate higher than the data rate of this signal. So you send it to the receiver, then the receiver is going to use the same process to recover the original signal. So the receiver is going to take the signal you send to him or her, and then it's going to generate those specific codes, spreading codes that were assigned to the signal. Use those codes to get the original one. So this is how spread spectrum is done. Thank you.